Okay, so this is going to be my tubule framework for renal physiology, and I'm just going to get into it because I want it to be available as people are starting this unit. So basically, it's all. I think the most important thing in renal for the renal phys test is to be able to draw the tubule and its parts. So first we draw the glomerulus, then we draw the tubule, and I'll show you how to draw the tubule. So it's basically, you draw the two distal tubules, proximal and distal, the two convoluted tubules, proximal and distal. You just put a loop between them, and then you add the collecting duct, and you're done. So to make it easy to remember and to draw, you can look at it as it's perfectly symmetrical, right? It's just this U thing with one weird part on the left and one weird part on the right. Now, of course, this glomerulus is not actually part of the tubule. When you get to path, you'll learn about glomerular diseases versus tubular diseases, and it's the two parts of the nephron. So this overall thing, when I say draw the tubule, technically what I'm drawing is the nephron, because the tubule is only this part, and then the glomerulus is, or the Bowman's capsule, is this part with the glomerulus inside it. The reason I'm not really being specific about that is it kind of doesn't matter. I just draw this so that it looks right. But honestly, the part that we're actually dealing with is this for this tubule stuff. So we have our proximal convoluted tubule and our distal convoluted tubule. We have our descending tubule because, of course, it goes down when you're going, and then it goes up. So we call it our ascending tubule. And then the caveat here is that there's actually two distal tubules. So it can help to draw it as a kind of like a butt cheek type thing so that you can remember that there's two. There's an early distal and there's a late distal. And then this last part, this big part at the end, is the collecting duct. So the really helpful thing here is that we split the tubule. It's 6 parts, right? 1, 2, 3, 4, 5, 6. We split it into 3 pairs. So 1, 2, draw a line. 1, 2, draw a line. And then 1, 2, that's the last pair. So before I get into the 6 pairs, I'll talk really quickly about absorption and secretion. So with everything in my mantra for all of physiology is that your blood is you, meaning the blood is the patient's body, right? So what I mean by that is whenever you want to know what's going on with your patient, you take a blood test, whether it's a CBC, complete blood cell count, or a BMP, basic metabolic panel. You're always looking at their blood. Whenever we talk about diseases, we talk about emia means blood, right? So we talk about hypoxemia, hyperlipidemia, hyperbilirubinemia, hypercalcemia, hyponatremia. Everything is always about the amount that's in the blood. So the blood is the patient's body. The blood is the center point for everything. Versus the lumen is actually not part of their body. What do I mean by the lumen? I'm talking about when you're dealing with different tracts, like the GI tract. The lumen, where the food is not actually part of the patient's body because it's continuous with the outside world. It's open at their mouth and it's open at their anus. So it's kind of like this tube that's just like this empty space. It's not really part of their body. The food is not really in their body until it's been absorbed into their blood. That's what I'm getting across. So whether it's GI, in GI, the framework is blood versus food is what I call it, meaning the blood versus the intestinal lumen. In respiratory, it's blood versus air, meaning it's the blood vessels versus the alveoli, the respiratory lumen. And then in renal, we have blood versus pee, and I draw the pee like this with dots in it. And that's just the blood versus the tubular lumen. So if we draw this tubule, it's going to look like this, right? The tubule is full of pee, right? And then outside of the tubule, you have blood, which are what we call peritubular capillaries. They're just blood vessels that are around the tubule. That's why they're called peritubular. So whenever something moves, because your blood is you, whenever we say the word absorb, your body is absorbing something, we're always talking about it's going to the blood, not leaving the blood. Because when you absorb it into your blood, you're absorbing it into yourself. The opposite of that is to secrete, when it's going into the lumen instead of the blood, right? So this is absorbing into the blood. This is secreting it out of the blood. Entering the blood, leaving the blood. So this is absorption, you're entering the blood, and the opposite is secretion, when you're entering the pee. Though that pair is the most important pair of language when you're talking about the tubule, absorb versus secrete. There's another pair that's also important, but not as much, but still important, and that's filtration versus excretion. So excretion is easy. It obviously means like what's going out into the toilet, right? So it's what has made it all the way through the tubule. That's excretion, what you actually pee out into your toilet. Versus filtration is about what's entering the tubule in the first place. It means that it's passed through the filter. Remember I told you that this is the tubule, but this part at the beginning is not part of the tubule. It's the doorway to the tubule. It's the entrance to the tubule. It is a filter. It literally filters all of your blood. So all of your blood gets filtered through this filter, and then all the good parts of your blood that you want to keep, your body absorbs them. So they get moved right back into your blood. But then the parts that your body doesn't want to keep, those ones can stay in the tubule or even get secreted back into the tubule so that you can pee them out. So filtration versus excretion is the beginning versus the end of the tubule. To start versus finish this marathon. But even more important are these two guys, absorb versus secrete, which means blood versus pee. So now that we have that put down here, we can focus on our pairs. Our parts of the tubule, our 6 parts, and we split them into pairs. So what's this first part? Well, actually I'll just number them. Okay, so the first part is the PCT, and the second part is the descending tubule. Third is the ascending. Fourth is the early distal. Fifth is the late distal, and then 6 is the collecting duct. Now, each of these 3 pairs has something unique about it, and that makes it really easy to remember. Also, each of these pairs has the same relationship between the 2 things in the pair. So we know that a pair, I'm always saying it's a yin yang, right? So the yin yang here is that you have the leaders versus the followers. In every pair, the first one is the leader in these pairs, and then the second one is the follower. Okay? Leader, follower, right? What do I mean by that? The leader basically does more work, and then the follower does less work. And that relationship makes it easy to remember what the different parts do. When I say work, I mean moving solids, right? Moving ions, right? As opposed to just moving water, which doesn't count. We're not counting that as work. So let me tell you what I mean. PCT is all... This pair, I'm going to say the relationships first. Leader versus follower. For the first pair, it's all versus nothing. Second pair, it's 4 things versus just 2 things. So the leader's doing more. 4 is more than 2. And then in the last pair, it's 2 different things versus just water, which is basically nothing. So I use like my water or the water symbol when it's only moving just water. So here we have an all versus nothing relationship. What do I mean by that? It means that the proximal tubule, it absorbs pretty much every kind of ion, and it does the most absorption. So it absorbs sodium, potassium, chloride, magnesium, calcium, phosphorus. It's literally just doing everything. Whereas these other parts later, they absorb more specific things. So the hardest working part of the tubule is the proximal tubule, because the way it works is when you're moving through this tubule, at the beginning, you're just absorbing everything. Like you're doing like very general, wide sweeping work, versus at the end, that's where you get specific and start really precisely honing what you want to keep in your blood versus what you want to keep in your pee and get rid of, right? So it's like very general work is at the beginning, and then very precise work is done at the end. You start very rough and loose, and then you get precise. So the very first part of the tubule is the hardest working. It moves the most things. It absorbs the most different ions, and I don't remember the percent, but it's like 60% of your all your absorption is done in the proximal tubule, like a huge amount of it. So the important high yield things to know are that it absorbs everything. Is that it absorbs everything, and that it's the one that will become ischemic first. This when you have shock or something like that, the proximal tubule is the first part that's most susceptible to becoming ischemic. Why? Because it's the most hard working. So it requires the most oxygen. So that when you're lacking blood and you're lacking oxygen, it's going to be affected first. So I just call him the most hard working part of the tubule. In contrast to that, his follower, the descending tubule, is literally the most lazy and most useless part of the tubule. It basically doesn't do anything. It doesn't move any ions. It just allows some water to leak through, and that's all. So there's the water droplet. So that's the first pair, and I call them the extreme pair or the simple pair, because they're very simple. It's just two extremes. You have the guy that basically does everything, and then the guy that basically does nothing. Next up, we have these two, which I call this. It's basically these two transporters. So when you're looking at the first and the last pair, you have the leader does a lot, and then the follower just moves water. Same here. Leader does a lot, follower just moves water. But in the middle pair, that's where it's more kind of complex, I guess, where they both do something. It's just that this second one, the follower does less. So it's 4 versus 2. So I call this the quad, and then I call this the salt symport. And those nicknames are important because they help you remember what they do. Why do I call this the quad? Because it moves 4 things. It's basically just a sodium-potassium pump, but then instead of just those 2 things, you have to add 2 other things to balance it out. And those 2 things are both chloride ions, but I like to write them separately because then you can easily see that it's 2 pluses and 2 minuses. And so it's balanced, the charge. So basically just think of it as a sodium-potassium pump, which is the most generic and famous kind of pump that you learn about in, biology and stuff like that. And then just add on this extra pair to balance out the 2 positives. That's how you get your 4. That's how you remember which 4 ions are being moved by this transporter. And they won't write it like this. They'll write it as this, right? NaK2Cl. But I remember it like this because it's, makes more sense. So that's that. And then for here you have the salt symport. NaCl is table salt, right? So that's how I remember that the 2 things that are being moved are Na and Cl together, and they're being absorbed. So the last part is this guy, who I put a star beside him because he's the most special and most unique part of the tubule. Why is that? 2 reasons. 1, he's the waste man. What does that mean? It means that his job is to get rid of waste, get rid of trash. He's the garbage man. Everything else here is trying to keep things that are good, not really get rid of things that are bad. So all of these are absorbing. You're absorbing all of these. You're absorbing all of these. But in this one, you're secreting things. And the 2 things that you secrete are the 2 types of waste that your kidney deals with. That's potassium and hydrogen. Potassium, why is it considered waste? Because if you have too much of it, it's really bad for your heart and it causes arrhythmia. So you never want your blood potassium levels to be too high. Like even if they're a little bit too high, it's a very big problem. So this is waste. Why is H plus waste? Because what the other name for H plus? Acid, right? And your body's all about trying to avoid being too acidic. That's why you have bicarb, which is another one of the things that's absorbed in your proximal tubule, because it absorbs literally everything. Infinity sign is here for that, to show everything. So you try to keep base because it's a buffer. It helps to prevent you from being too acidic. So even though this is oversimplification, obviously, I view base as a good thing that your body wants to keep, and I view acid as a bad thing, a waste product that your body wants to get rid of. That's why when you exercise, your body produces lactic acid, right? It's a waste product. So these are the 2 waste products, and the waste man handles both of them. That's the late distal. And then at the end, you have the collecting duct, which just moves water. But it does it through these aquaporins. So it's like ADH will work here. And so it's moving water like in a more substantial way. compared to this useless guy that literally doesn't do anything. The water it just allows the water to leak through, right? So even though they're both followers, the collecting duct actually is kind of important. Whereas this follower, the descending tubule, is like so useless. Anyways, obviously it's not really useless. I'm saying, over big picture. So the other thing that makes this late distal tubule so unique is that not only is he moving two different things, it's two different transporters. He's the only one that has two transporters. This is one transporter that moves four things together in the same direction. This is one transporter that moves two things together in the same direction. But this is actually two separate transporters, and they're both antiports. One is a sodium-potassium antiport, and the other is a sodium-hydrogen antiport. So it's the only part of the tubule that has two different, important main transporters that are both doing their own roles. So I say this is a simple pair at the top. This is a more complex pair because it's not just an important one and a useless one. It's like they're actually both doing something. And then I say this is even more special. This pair is even more special. Why? Because it has this guy, the wasteman. So the other thing that's special about this last pair is that even though I split them up and our class splits them up into late distal and collecting duct, a lot of sources treat them as if they're the same thing. So a lot of sources will just call these two together the collecting duct, which can be kind of annoying. But the reason is because, let's say the wasteman is yellow, right? The wasteman is here, right? Versus the aquaporins for the collecting duct are here, right? That's true. But the way this works is that there's a lot of overlap to where some of these wasteman transporters will also be in the collecting duct, and some of these aquaporins will also be in the late distal tubule. So there's enough overlap to where they're basically kind of, the same region. So basically, if you're using a source and they say early distal and late distal, then they're describing it the way we do. But if they just say distal and they don't specify early versus late, you should assume they're talking about the early, because that means they're treating the late distal as just part of the collecting duct. So some sources will use the word collecting duct to refer to both of these, okay? It'll use the word collecting duct to refer to this whole last pair. And you just have to know that the wasteman transporters and the aquaporins are all in that quote-unquote collecting duct area. So we have three pairs. Our simple pair is first, then we have our complex pair in the middle, then we have our even more special pair at the end. So basically, I would say that these three parts of the tubule are the three most important parts that you talk about the most, especially in farm, right? You have this pair. This is the most important pair or the most important duo, but then this is the most important singular part of the tubule, this late distal. So that is that. Now, how do you remember that this is absorption, that these two are absorbing and not secreting? It's because, first of all, these are both symports, so they're moving all of the things in the same direction, the ions. And, right, they're not antiports. They're not moving them away from each other like this. The other thing is they have sodium in it. So the really important rule is that sodium is gold. Sodium is like the most important, most valuable thing ever to your body. So something that we're going to talk about in class is how salt used to be used as currency because it's so important and so valuable. So like back in the old days, Roman, Greek, or whatever, Egyptian, salt was used as a currency. Salt was like money. Because salt is so valuable for the human body, it was also so valuable in human societies. Because if you didn't have enough salt, you literally will die. So when I say salt, of course, I mean as in, I'm referring to sodium, not necessarily NaCl. But basically, if salt is part of the mix, you're absorbing. Because at every part of the tubule, your goal is to absorb salt. You absorb salt here. You absorb salt here. You absorb salt here. You absorb salt here. You absorb salt here, right? So that's something that everybody wants to do, absorb salt. And so I have three categories of things in your tubule. I have yum versus yuck. Yummy versus yucky. Yummy are the things that your body wants to keep. They're going to go to the blood. Yucky is stuff your body wants to get rid of. It's going to go to the pee, right? So the reason I have this here is that the caveat is that there's one thing that's even more valuable to your body than salt, and that's sugar. So I call it super yummy. Sugar, your body is going to absorb 100% of it. Whereas salt, your body, because it's so valuable, your body absorbs 99%. But sugar is 100%. That means you should never ever see sugar in somebody's pee. If you do, that automatically means they have diabetes, because their body should be trying to keep all of the, or their body is trying to keep all of the sugar in the blood. So these things are two very valuable things. But even though sugar is even more valuable, that's why we have like obesity and everything in modern day, because our brain is programmed to always want more sugar no matter what, right? Because it used to be so important for survival. But the more important thing that you spend more time talking about is salt here, okay? And then yuck is like waste products, creatinine, BUN, whatever. So like, or I guess like the H plus and K plus. So why am I talking about salt? Because you're always absorbing salt, right? So when you get here to the waistband, you know these are antiports because they're going to absorb salt into the blood and get rid of the waste into the pee. So they're moving the two things in opposite directions. Good. So I guess I'll list the hormones too that work at each spot. Basically, at the beginning, you have angiotensin, who I call Angie. And then here you have her little brother, aldosterone, because when you're doing your RAS system, you have renin, the dad, Angie, the big sister, and then aldosterone, the little brother. And they activate each other, right? So the dad activates the big sister activates the little brother. So they're both A and A, Angie and aldosterone. So Angie's going to work here at the PCT. She's also going to work in these afferent and efferent arterioles even before you get to the PCT, and I won't explain that, but the whole point is just that Angie's at the beginning, whereas her brother Al is right up near the end. And then the only thing that's even more at the end than Al is ADH, which also starts with A. So it's nice. The tubule, the beginning and end of the tubule are just A. Angie, aldosterone, ADH. AAA. And then in between, this guy doesn't have anything because he's useless. He doesn't even do anything. So why would he have a hormone there? This one, it's not really a hormone. Rather, it's a drug that acts on it. So you have loop diuretics act on your ascending loop, right? Wait, it's called loop. How do I know if it's the ascending loop or the descending loop? You know it's ascending because the descending is useless and does not do anything. So why would there be a drug for it, right? So loop diuretics act on the ascending loop. And then thiazides act on the, this part right after, the salt symport. And then the unique thing here is that your thiazides are calcium sparing. So they also, let you absorb calcium so you don't lose it in your pee. And then aldosterone, you have your spironolactones. You have your potassium sparing. As opposed to calcium sparing, they're potassium sparing diuretics. And the whole point of these drugs is that they're blocking the normal function. They're not helping the normal function. They're trying to reverse it. So since the whole point of this part and the aldosterone is to get rid of waste, to get rid of potassium, a drug that blocks that is going to be potassium sparing. It's going to cause you to keep potassium in your blood instead of getting rid of it and peeing it out. So the main one is spironolactone. Anything that ends with "one," that's steroid, right? Aldosterone is a steroid. So the drug that blocks it matches its name. They both end with "one." And then ADH is a hormone, antidiuretic hormone. Antidiuretic means don't pee. And Dr. Carroll calls it water-conserving hormone, which is really awesome. And I definitely recommend calling it that and never say the word ADH again, because water-conserving hormone is a very helpful way to think about it. But basically, those are the three pairs, right? The three parts of the tubule, which give us the 6 parts of the tubule. The other thing I'll talk about then is the values that you have to memorize. So I had a nice mnemonic for that. I call it the rule of 4s. Basically, you have your thing where you have to, memorize these numbers, right? So first of all, you have to be able to draw this box with the names, and then you have to be able to draw the box with the numbers. And I'm going to show you how to do that. So To draw the box with the names, because it has to be in the right order, right? The way you do it is that you have couples, right? Positive ions are boys, negative ions are girls, and these are all straight couples. So boys go with girls, right? So NaCl is table salt. This is a very famous couple that everybody knows, right? So it's going to be easy for you to remember when you're starting your table to put NaCl, to put the Cl after the Na, right? And they balance each other out perfectly because one is positive, one is negative. After that, you're going to put K and his girlfriend. Now, there's a relationship here where when you compare the left to the right, you're comparing positive to negative, right? But when you're comparing the top to the bottom, you're comparing rivals. So it's couples versus rivals. Couples move together because they like each other, right? So like if you had a symport, the Na and the Cl would both move the same way because they're a couple. But when you do your sodium-potassium pump, it's not a symport, it's an antiport, right? They hate each other, they're rivals. These two guys hate each other and they're always trying to fight. So the Na goes one direction and the potassium will go the opposite direction. So it's, opposites attract type thing, and then the same charge they repel. You can think of it like that. So I call it like the boys like to fight each other, and then the couples like to go out with each other. And then I call it cat fight. Yeah, sorry, but it has to be memorable. So for the two girls, I call it cat fight because they also go opposite direction from each other. And sometimes that's not as important as the two guys, but that comes up as well sometimes too. So they go opposite from each other. So good. Now that you remember the order to draw the names in, you have to draw the numbers in. So that's the rule of fours. So just like we had two pairs in this square, right? Because that's the whole point of the square. The top was the famous couple, and then the bottom I call them like the emo couple or whatever, the dark. And then the left was positive charge, right? Left side, whereas the right side was negative charge. So we can compare it left versus right, or we can compare it top versus bottom. It works both ways. We're going to do the same thing here with the numbers. So the top pair is the big pair. Versus obviously has to be small, right? That's the whole point of the verses. When you know one thing, you automatically know the other thing. So if the top pair is big, the bottom has to be small. What do I mean by that? Basically, the big means it's triple digit, right? Small means it's less than that. It's not triple digit. So the big pair are in the hundreds. So my rule of fours is you have 140, then you have minus 40. Then for the small, you have another 4, but it's not 100 this time. It's just a small 4 by itself. Then the last one, you have 1/4, 1/4, a quarter, which is 0.25. But of course, it's not 0.25, it's just 25. So it's not really a quarter, but it's just to help remember it. So the way the rule of fours goes is it alternates. On your big pair, you have a 4 thing, and then you have a thing that's not 4. Then for the small pair, you have your 4, and then you have a thing that's not 4. So it's even though I say not 4, it's like a fake 4, because this one is minus 40, right? It's you had 140, then you do minus 40. So it is kind of 4 in a way. It's just that you can't see it. It's an invisible 4. Then this one, you see the 4, whereas this one, it's 1/4. So it's 4 related, but you don't see the 4. So it's 4, invisible 4. 4, invisible 4. And so that's to remember, the values for sodium, chloride, potassium, bicarb, right? After that, we can now add on the waste products, which you can have as a separate thing, or you could add it on to the bottom of this, doesn't matter. And the waste, and I'm not talking about potassium and hydrogen waste, I'm talking about creatinine and BUN. The way this works is if your creatinine and BUN are high, it's just a sign that your kidneys don't work. That's all it means. It just shows that they have kidney disease. And that's what that's used for. So it's important to know that creatinine starts with C, and when they say BUN, it means blood urea nitrogen. But sometimes people will just call it urea. So do not look at it as starting with a B. You have to look at it as starting with a U, right? It's not BUN, that's just an abbreviation. It's actually just urea. C comes before U. And you could also say when you turn a C, it becomes a U. Why is this important? Because you need to have them in the right order to remember the values. So this is my rule. The rule I have for this is 6, 7, 8. What do I mean by that? I mean, first you write a 6, then you write 7 and 8. Now, it's a similar relationship where just like it was big versus small, the first one is going to be smaller, and this one's going to be bigger. Obviously, 7 and 8 are bigger than 6, right? In addition to that, we're going to make the small one even smaller because we're going to make it a decimal point. So for the 6 side, it's going to be 6 to 12. This one's going to be 7 to 8. Because when you double 6, it's 12, right? But instead of it being 6 to 12, it's actually going to be 0.6 and 1 to 1.2, right? So we made it smaller with that decimal. Versus on the other side, we're going to make it bigger by turning the 8 into an 18. Because 7 to 8 is literally a range of only one difference. Obviously, we're not going to have that. Why would we have that, right? It needs to be like an actual range that's substantial. So it's 7 to 18. So these are the ranges for creatinine, normal levels of creatinine and BUN. 0.6 to 1.2, and then 7 to 18. But I just use this rule of 6, 7, 8 to make it easy to remember. And then if you just remember that this one is going to get bigger by turning 8 into 18, the big side's going to get bigger, and then the small side's going to get smaller by adding decimals to both of them, then you're good. And of course, 6 times 2 is 12, so that's why it goes 6 to 12. So 6, then 7 and 8. And those are your waste products, your creatinine and BUN. So those are the values that you have to learn. And I think that made it really easy. Of course, it's plus or minus, so I'll add that part in. So like, what's the range for normal sodium? It's 140 plus or minus 5, right? They're all plus or minus 5 by default. This one is not, the 4, because it's so small, obviously it can't be plus or minus 5. So it's plus or minus 0.5, right? Which means it ranges from 3.5 to 5. Yeah, okay, that's not even, so you're saying like, okay, it's minus 0.5, but that's not plus 0.5, that's plus 1 to get to 5. Well, it's literally a 5 though, so it just matches the vibe of 5, you get what I'm saying? So, even though it's not actually exactly plus or minus 0.5, just know that it's going to be 5 and 5, right? Like 3.5 to 5, right? It's on the lower end and the higher end, it's 5. So it still matches this vibe of like 5, okay? And then this is also plus or minus 5. Or I think it's plus or minus 3. Because the last one is like the weird one, right? It's the odd one out. Because it's not even like 4 related. It's just like 1 over 4 trig. So this last one is always the weird one. So instead of plus or minus 5, it's plus or minus 3. And that's that. But, you know, the overall thing is to be able to get like, just remember the overall range. So if you thought this was plus or minus 5 instead of 3, you'd probably be fine, but whatever. Yeah. So there it is. Yep, I think that's it. So basically, of course, you still have to learn the stuff you're going to learn, but the idea is that this tubule framework just makes it way easier. And then you have to memorize these numbers, so it's nice to have a mnemonic for that. So last thing I'm going to do is show you on the thing how these are grouped up. So this main pair, you see how, and I actually should have numbered them. So I have them labeled, and I'm going to number them now. 1, 2, 3, and I'm going to even erase the names, because that's how I actually do it. I just use the numbers. So you can see how there, when you label it yourself or number it yourself on the drawing, it's like a vertical and type of relationship. So like, it's like when you're trying to imagine this in your head, you need to be able to imagine it quick and easy. So just know that the first pair are like one on top of the other, right? It goes down. Like to get from PCT to the descending, you go down. Go down. Then for the second pair, you go up. Then for the last pair, they're just side by side. Because they're the pair that's kind of fused together, right? It's like distal, tubule, late distal and collecting duct are kind of the same thing. Yeah. And then when you're doing your farm and stuff, you basically will ignore this first pair. So then it becomes even easier because it's just 2 pairs or 2 parts of the tubule. It's like this part versus the last pair. Second pair versus, or the middle pair versus the last pair. So last thing I'll do is that you need to, obviously you can just label them and count to know where to draw the dividing lines, but I will also just show it. So a friend of mine realized that a good way to remember it is that you cut this, because it's like symmetrical, right, with this U, you cut the U in half, and then you cut the distal tubule in half. Why? Because you have two loops and two tubules, and two distals, right? You have your descending and your ascending loops, that's two parts of the loop, and then you have your early and late distal tubule. So those are the parts that you cut in half. So cut your loop into the two loops, cut your distal into the two distal, and then you have your tubule, and you can just number the pairs. So that's it. My Uber is here.